Hello, everybody, and welcome to Chapter 4, Vector Spaces. Vector Spaces, this is where it really starts getting real, or I should say more abstract, as a mathematician. In other words, what am I trying to say? Vectors, it's a funny thing. I guess all of math, the way a mathematician would think of vectors versus the way an engineer would think of vectors versus the way a physicist would think of vectors is often different. We all use them, we all study them, but the way we view them and approach them is a little bit different. And that's really true of matrices as well. And that's true of differential equations. That's true of pretty much anything, calculus, the way we view math and use math and so forth. Anyway, vector spaces, these are a whole bunch of sections. And we're going to start with the first one, 4.1. And 4.1 is going to give you a more physical description of a vector. So a lot of you probably like that. Here's, I like the way the book always has different applications. This one I find interesting, the morphing one. Of course, I don't need a computer for this. This could just be before my coffee and after my morning coffee, but that's the way it works. Anyway, so let's start with 4.1, vectors in Rn. So we think of we visualize vectors often as not just a line segment, but a direct line segment, meaning a line segment that goes in a specific direction. So we can think of, we'll look right now, we're just looking at vectors in the plane. But now we're going to see mathematically vectors can be viewed a whole different way, but right now we're looking at it just more of the way a physicist or an engineer would look at a vector. So it's a directed line segment, and the initial point, we generally place the initial point at the origin, and the terminal point, we place it somewhere in the plane, wherever it goes, and we draw an arrow from the origin to that terminal point. So in this case, the terminal point is x1 comma x2. And remember, you would normally call this x comma y, but we're calling it x1 comma x2 because, like I said, you can have 47 variables, not just 2 variables. But for now, x1 comma x2. And there's an interesting side point. You see it's written right here it's written right over here. I find it very interesting that the term vector comes from the Latin word vectus, or vectus, I don't know if I'm pronouncing that right, which means to carry. So the idea is that if you're going to carry something from the origin to the point x1 comma y1, then the trip could be represented by a directed line segment from the origin to that point. I found that kind of interesting and I found it noteworthy. So usually in this textbook, we represent vectors as bold, small letters, not capital, but bolded. So the bold U, the bold V, the bold W, and so on and so forth. That's just again just some notation that we're going to be using if these now the x1 and the x2, the variables that go inside, we call those the components of the vector, and the and two vectors are equal if and only if their components are equal. Similar, by the way, to two matrices being equal if and only if the entries are all equal, and not just equal but analogous, meaning u1 equals v1, u2 equals v2. I can't have u1 equal v2 and I can't switch them. I can't say 3 comma 5 is equal to 5 comma 3, just like I can't say that with a matrix. By the way, you could think of a matrix, or you could represent a matrix you could represent a vector as a matrix. You could represent a vector as just a single column matrix or as a single row matrix. You just think about that. Anyway, let's look at some vectors in the plane. So here we have, so we want to represent the vector 2, 3. And what we do here is that we have an arrow from the origin up to the point 2 comma 3. And here we want to represent -1 comma 2. So we draw an arrow starting at the origin up to the point -1 comma 2. And this is just the way we represent vectors. We often represent vectors, or I should say, this is the way that we can represent vectors in a plane. Okay, now vector operations, as you're going to see, are pretty similar to matrix operations, not that much different. So one of the basic vector operations is vector addition. And again, we're going to see this, as you'll see, this is very similar to matrix addition. Vector u plus vector v. So we take u is u1, u2, v is v1, v2. And when we add them, we just add the first component, comma, now the sum of the addition of the second components. That's very, very similar to the way we had, in fact, exactly the same as the way we had two matrices. And of course, if you have a vector which is 0, 0, then that's just the zero matrix. Just like we had the zero. I keep saying matrix. That's the zero vector, just like we had the zero matrix. By the way, if you notice that when I add two vectors, here's u, here's v, here's u plus v. It always winds up being this. You wind up getting this kind of parallelogram action going there, which is kind of cool. And that's very easy to show. That's very easy to prove that's always going to be the case. Now, when we add, so let's do some examples. Let's look at some examples here. Actually, I should let you pause your video. Oops, I showed you the answers. So find the sum of these vectors and pause your video, work it out. Okay, now you can unpause. Let's see what you got. And here's what you should have gotten. The 3, 2 should be your final answer. This should be 0, 0. Now that means these two vectors were additive inverses of each other, and which of course is the 0 vector, and 2, 1. Now notice that what I did here is I took 1, 4 to look at this in a picture form, and I took pictures, yay! And I took the second vector and I added them. I got 3, 2. But you see, if you draw it out, you get this little parallelogram. Now here, of course, you're not going to get exactly. Well, here you're going to get a squished parallelogram because one vector is going this way, the other vector is going that way. When I add them, I just go right smack in the middle. And here I added the 0 vector. So I started with 2, 1. I added the 0 vector, but all I got is just 2, 1. So these are a little bit different. I don't know what kind of parallelogram that will be, but it's, obviously, give me a little slack here. So let's move on. And just like in matrices, we had scalar multiplication. Well, in vectors, we also have scalar multiplication. So vector, if v is a vector v1, v2, so I can multiply that by a constant c, and then the constant just goes into the vector. Exactly the same way we did with matrices. Exactly the same. And I can multiply by the scalar of -1, and I get negative v, which is going to be the additive inverse. Again, just like we had with matrices. And I'll call negative v I'll call that negative v, and in this case, I'm going to say v is subtracted from u. That's what I mean by subtraction, when you add the negative, just like with anything else. Now, the vector -2, 5, and u is the vector 3, 4, then let's find 1/2 v minus u. I shouldn't be showing you the answer as well. It's too late. 1/2 v plus u. So v is equal to -2, 5. 1/2 v is just 1/2 of each thing, which is -1, 5. You don't necessarily have to go through all of these steps. We just, sometimes the textbook just shows you a lot of steps just so it's crystal clear. But like, again, this is kind of not well, that's up to you. Anyway, for the next one, subtraction means I'm adding the negative. So this is going to be 3 minus -2 and 4 minus 5. See what I'm doing there? And I get 5, -1. And finally, 1/2 v plus u. Well, I take, this is cool. I already know from A what 1/2 v is. And now I know it, but I know what u is because that's given. And I add them up. -1 plus 3 is +2. And 5/2 plus 4 is 13/2. Now, if you'll notice, there are 10 different things that you could do with vector, 10 different properties of vector addition. And we're going to use these 10 properties to define something called a vector space. But we'll get to that in 4.2. Anyway, but that's a big thing, vector spaces. Anyway, we see that what does this mean? This means that it's closed under addition. If I take a vector v and u and a vector v and I add them, the result is still a vector and it's still in the plane, and that's closure. And that makes sense. If you just think about it, if I add two vectors in a plane, it makes sense. The parallelogram is going to stay in that same plane. Here we see it's commutative. Here we see it's associative. Here we see that you have additive identity, additive inverses. You know, these are very make common sense. They basically make a lot of sense, and we see distributive property, and this is very similar. We had these very similar properties to this in matrix addition. And as you'll see, there's a lot of connection between, and here it works out. Here you just see it. Why does associativity work? Because basically I just decompose it into its components, and the components are just regular numbers. The associative property works. It's all cool. So here's the proofs here. I'm not going to go through them. They're kind of easy. Alrighty, moving on. Now, RN. What does RN mean? That does not mean registered nurse. RN, which is a term we're going to use a lot, means the ordered n tuples. In other words, when you have the plane, that's really ordered pairs. You've heard that expression many times, ordered pairs of real numbers. When you have three-dimensional space, that's ordered triplets, or ordered triples of real numbers. What if you have 4 dimensions, 5 dimensions, 6 dimensions, n dimensions? That's n tuples of not ordered. That's a ordered n tuples. Now, a lot of my students start freaking out at this point, because what does it mean 4 dimensions? I understand a point. You know, I understand. You know, 1 dimension is a real line. It's just a straight line. 2 dimensions is a plane. 3 dimensions is space. What's 4 dimensions? Well, an n dimension. What does that mean? So a lot of my students at this point start like freaking out. And I just want to say, don't think of dimensions. Don't think of it as space. Dimensions just means different variables. Like, for example, if you want to talk about the weather, so there's a lot of variables, and figure, and you know, there's temperature, and there's wind, and there's humidity, and there's barometric pressure, and there's all kinds, you know, I don't know, all kinds of stuff when it comes to weather. There's a whole. I'm not a scientist, or a weatherologist. What do they call themselves? But you know, there's many variables. So if you want a formula, you know, talking about with weather, you may have many variables. In fact, that was actually historically a little historical note here, and this is even before my time, when they were working on the first computers. This is like in the late 40s or 50s, when they were working on computers. So one of the challenges, they call it the ENIAC and the MANIAC. Not MANIAC like crazy, but it stood for something. You type in MANIAC computer in Google, you'll see a whole thing about it. They would actually, so they wanted to test the system. They wanted to test that this phenomenal new computer worked. They wanted to give it some challenge, and they used the computer to calculate, to figure out, predict weather, basically. And that was because that's a huge challenge. There's so many variables when it comes to, you know, weather. Anyway, an n tuple can be viewed as a point. I'm doing air quotes now in Rn, and the xi's are the coordinates of or you know, or components of it as a vector. Anyway, let's move on. So here's x my vector. Now, the definition of vector addition. Here we see vectors in 3 dimensions. The definition of vector addition and scale multiplication in Rn, it's the same definition. It's just that now when I add u plus v, it's u1 plus v1, u2 plus v2, u3 plus v3, up to un plus vn. Again, don't try to visualize this spatially, because in space is only 3 dimensions, but just think of it as a whole bunch of variables. And cu, bye everyone, get it? Is cu1, cu2, just like we said a few minutes ago with you know, ordered pairs. Works the same way. And everything is kind of, you know, pretty much everything is the same. If here's a three-dimensional vectors, right? R3, we call it R3. And when you add u plus v, you just add -1 plus 2, 0 plus -1, 5 plus 1, and you get 1, -1, 6, all the way down the line. It's all the same. It's the same thing. Same old. And now we have the properties of, now what I'm showing you right now on the screen is exactly the same as what I showed you a few minutes ago Only there we were saying it for just, I think for just for the plane. Now we're saying it for all Rn. So this is literally the same thing I just showed you a few minutes ago. But this is, and as you can see, it is the same thing because you add vectors the same. What's the difference if you have two components or 27 components? It's the same. It's the same process. And just like matrices, when you add matrices, you know, it's what's any size, it works out to be the same. And let's look at some vector operations here. So U is this vector here, V, so this is R4, W is this big vector over here. So we just want to say, we want to just calculate here. We want to find 2U minus the parentheses V plus 3W, figure that out. And then we want 3X plus W. Once we found this new vector X, now take 3 times X plus W. I'm sorry, I read it wrong. A and B are independent of each other. So here we want to find X by just doing these operations. Here we want to find X by also kind of doing these operations and just solving for X. All right, pause your videos. All right, you're out of pause. Let's see what you got. So this is this is what A should have gotten you, and this is what B should have gotten you. And just follow these steps. So 2U is 2 times that, which gives me this guy right here. I'll distribute the negative just like with regular, you know, subtract regular whatever, because the distributive works. And so now I get minus the V vector and minus the 3 W vector. And now I just simplify all these and I add them. I just, now I'm just going to add each component by component. So 4 minus 4, don't forget there's a negative there, minus negative 18. So that's 4 minus 4 plus 18, and then so on and so forth until I finally get 18, comma negative 11, comma 9, comma negative 8, which is what you should have gotten. And for B, what we're going to do is we're going to say 3 times X plus W is equal to this. Now, what we're going to do here, and you don't have to do it this way. You could at this point stick in all the different coordinates, but what we're doing instead is we're going to solve for X, sort of like it's an algebra. Think of these like algebra variables. So we're going to distribute the 3, and we have an X on this side, so we're going to subtract X from both sides, literally like we're doing an algebra equation. We're going to bring the 3W over to the other side, just like algebra, and we say 2X is equal to this, and X is equal to that. And if you notice, we're so nice that this 2U minus V minus 3W is exactly what 2U minus V minus 3W is exactly what we figured out in problem A. So even though problem A and problem B were technically independent problems, it turns out we were nice enough to make the solution of A help you. And if we didn't have that, we would just crunch this all out. That's just the way it is. Okay, moving right along. Here are some properties of, again, these are pretty much common sense. The additive inverse is unique. So if V plus U equals V, then U is equal to the 0 vector, meaning there's one and only one 0 vector. And the identity of inverse of V is unique. That is, if V plus U equals 0, then U is equal to negative V. Meaning there's only one identity. And these are things we actually did stuff like this with matrices. The scalar 0 times any vector V gives me the 0 vector. Any scalar C times the 0 vector gives me still the 0 vector. And if CV equals 0, the 0 vector, then either C equals 0 or V equals 0. That's it. There's no way I could take a non-zero scalar and a non-zero vector, multiply them, and get the 0 vector. So very, again, this is very similar to properties of real numbers. I mean, if I have two real numbers, A and B, if A, B equals 0, then either A equals 0 or B equals 0. If I can't have two non-zero numbers, multiply them and get 0. Just don't, it ain't going to happen. And the inverse of the inverse is just the original vector. And again, the proofs here are very similar to what we did with matrices. And let's see. So here we see if V plus U is equal to 0, we want to prove that U here must be the 0 vector, because V plus U equals 0. So what I'm going to do is I'm going to add the additive inverse to both sides. I'm allowed to do that. And then this, of course, on this side becomes the zero vector. And here I'm going to do commutative, switch the v plus u to u plus v. And now I'm going to do associative, where the parentheses switch, and v plus negative v, which is just 0. So u plus 0 equals 0, but u plus 0 we know is u and pow. So it's a pretty long, I shouldn't say long, but it's a proof. This is really a proof that that 0 is unique. And the rest of the proofs are similar. This guy here is trying to show that additive inverses are unique. So we want to show that if v plus u is equal to 0, then u must be the negative v vector. So what I'm going to do is I'm going to add negative v to each side. I'm going to add it on the. By the way, it's very strategic whether you're adding on the left side or on the right side. But either way, it's commutative, so it's going to work out. So I add negative v to each side, and what's going to happen is that I'm going to switch the parentheses around. The negative v's are going to cancel, become the 0 vector, and 0 plus u is just u. That's something we know from our definitions, our onset, whatever, our axioms, if you will, and probably 4.2, whatever you call it. Anyway, I hate when I do these live recordings. That's why I hate doing these things, because it's very hard. And I always say things, and I should say I hate them. I love doing these recordings, but it's so sometimes it's nerve-wracking. You say the wrong thing, and then everyone starts copying it down, and problem. Anyway, and here negative v plus 0 vector is just negative v, and that just kind of stays down the whole way. At the end of the day, u is equal to negative v, and pow. That's the proof. All righty. Well, that was loads of fun. This is something in physics. You've seen this. You've probably seen this kind of thing where you're dragging something up a hill, and the force. So it turns out the force is equal to W times sine theta, and you can kind of see it from this picture, because theta here, this angle here is by similar triangles, you can very easily see that angle there is theta. So F is equal to W sine theta. Force is equal to work times sine theta, meaning that you need more force to push something. The bigger theta is, the more force you need to push those. So it kind of makes sense. Anyways, now for a concept that's extraordinarily important in linear algebra, and that's the concept of linear combinations. Linear combination is something, it's a term you're going to hear a lot, linear combination. So if you have a bunch of vectors, v1, v2, vn, and a bunch of scalars, c1, c2, cn. So if I take a scalar times v1 and a scalar times v2 and dot plus a scalar times vn, and I add them all up, that's called a linear combination. So the resulting vector x is called a linear combination of the vectors v1, v2 through vn. So linear combination of vectors is when if I have two vectors, well, let's just look at an example. So x is this vector here, u is this guy there, v is that guy there, w is that guy there. So we want to express x as a linear combination of u, v, and w. That's interesting problem. So what are we going to do? Well, let's work it out here. X is that guy right there. So I want a times u, b times v, c times w. But think of it. Let's put this into one giant vector. A times 0 is nothing. B times -1 is negative b, so it goes right there in the first component. C times 3 is 3c. That goes in in the first component. So the first component of my resulting linear combo vector is negative b plus 3c. The second component, a times 1 is a, so I put the a right there. B times 1 is b, so I put the b right there. And c times 1 is c, so I put the c right there. Here, a times 4 is 4a, 2b, and 2c. So this is now we're going to match it up, because negative b plus 3c, if these two vectors are equal, then their components are equal. So negative b plus 3c has to equal that -1. A plus b plus c, which is in the second position, has to equal -2. 4a 2b plus 2c has to be, which is in the third component, has to equal that -2 right there. So I actually have now 3 equations to 3 variables. Solve those any way you want, and you're going to wind up getting a is 1, b is -2, and c is -1. And just solve this, and you'll see that. So therefore, I could say that my vector x is equal to u minus 2v minus w, which is a linear combination of u, v, and w. That's exactly what we're trying to do here. And sometimes it helps to express a vector as a row matrix, like I said before, a single column, row matrix, or a single, a single row matrix. So we call it a row vector. Sometimes we express it as a column matrix. So we call that a column vector. And it's all the same thing, meaning that whichever way I do it, whether I take this row vector and this row matrix and that row matrix and add them up, I get the same thing as if I take this column vector plus that column vector, I get this guy here, which is the same thing if I just do adding 2 vectors. And these 3 things are just 3 different ways of expressing the same thing. That's all we're trying to say. The only difference is just what they look like, but or the notation, the way they're displayed. Other than that, it's the same information. And that concludes 4.1. It's been a lot of fun, and we will see you guys in 4.2, and that's where things are going to start getting awesome. Well, it's already awesome. It's going to get even more awesome.